If an alien species were to visit Earth, the most objective way they could measure our progress is by looking at how much raw power we can harness. That concept is called the Kardashev scale. Right now, we score extremely low on this metric. We haven't even reached Type 1, which requires capturing all the available energy on our own planet. To understand what a Type 2 civilization looks like, you have to look at the center of our solar system. The Sun accounts for 99.86% of all the mass in our local neighborhood. Earth is barely a dust speck in comparison. The amount of energy from the Sun that actually hits the Earth's cross-section is roughly a half-billionth of its total output, and the fraction of that energy we currently capture is far less than a trillionth. As a solar collector, Earth is wildly inefficient. 70% of the surface is water. We are wrapped in a thick atmosphere that scatters incoming light. And of the 30% that is land, a massive chunk is made up of environments like Siberia or Antarctica, where you can't realistically build or maintain vast solar arrays. To support the exponential power demands of artificial intelligence and move up the Kardashev scale, we have to look past terrestrial grids. We have to start moving our infrastructure into space. Doing that requires breaking through 3 distinct engineering bottlenecks. The first constraint is getting the hardware up there. To capture a meaningful percentage of solar energy, you have to launch millions of tons of material into orbit. That is economically impossible if you rely on traditional single-use rockets. That is the exact problem Starship is built to solve. It is designed to be the first fully and rapidly reusable spacecraft. Think about the airline industry. If we had to throw away a Boeing 747 every time it flew from New York to London, flying would be too expensive for anyone to use. The Starship is designed to land, be caught by the launch tower, and fly again with minimal inspection. This chart shows the massive leap in orbital logistics we are looking at. Right now, humanity launches around 2,500 tons to orbit every year. Starship's design intends to push that capacity to millions of tons per year. Once you clear the mass-to-orbit constraint, building megastructures off-world stops being a theoretical physics problem and becomes a straightforward logistics operation. You still can't just slap rockets onto a terrestrial data center and send it up. Space is a vacuum, which introduces our second bottleneck, power and heat. The AI satellite is a flying battery and cooler supporting a 150 kilowatt server rack. A 70-meter wingspan of solar arrays absorbs continuous solar energy. Massive double-sided radiators oriented knife-edge to the sun shed the waste heat directly into the vacuum of space. To connect all this hardware together, these orbital racks communicate with each other and back to the ground using existing laser link technology, keeping latency incredibly low. By isolating the delivery of power and the dissipation of heat, engineers have outlined a blueprint for an infinitely replicable off-world compute node. That brings us to the final hurdle. If you want to deploy AI compute in space at the gigawatt or eventually the terawatt scale, you need a staggering volume of physical silicon and solar panels. The proposed solution for this hardware deficit is a massive dedicated manufacturing facility called a terafab, designed specifically to churn out AI chips, radiators, and solar cells. The proposed terafab covers 100 million square feet, a footprint that could swallow 10 giga-Texas plants. It represents a pivot toward the brute force production required to move beyond Earth's limits. With a facility like that, the final barrier to building space networks becomes a problem of brute force terrestrial mass manufacturing. Eventually, even a facility that massive will hit the physical limits of Earth's manufacturing capacity. To get to the next order of magnitude, the operation will have to scale to the moon. Building on the lunar surface offers significant physical advantages. You can manufacture the solar arrays and radiators using local materials in an environment with zero atmosphere and only 1/6 of Earth's gravity. Because of that low gravity, you don't even need chemical rockets to launch the hardware. You can accelerate the completed AI satellites directly into deep space using an electromagnetic mass driver, which is essentially a giant railgun. Migrating human compute power off-world and tapping directly into the sun's unfiltered output marks our first deliberate step into becoming a Kardashev Type 2 civilization.